Welcome, ladies and gentlemen. We are moving now into chapter 12, the beginnings of pendular motion or simple harmonic motion. So we're leaving behind electricity. You're done with that. And we're going to go back into things that move. We were doing things that move a while ago, and now we're going to be back into that. We're looking at something called simple harmonic motion, when things move and they keep doing that same motion, like the swing set, or like the pendulum on a clock, or a bouncing spring, or various sundry other examples. So when something starts moving and then it keeps doing that same motion over and over again. Periodic motion is motion that is repeated over and over in a predictable way and at a constant rate. And so, again, a kid on a swing going back and forth. That's periodic motion, right? Or a spring that's bouncing is periodic motion. Something that is repeated over and over in a predictable way. We can use the word oscillation to describe periodic motion. It's an oscillation between two extreme positions and a central position of rest. And so picture, you on a swing, or your little brother or little sister on the swing. And when they're all the way back, that's one extreme position. And then they go all the way forward, and that's another extreme position. But if you were to grab them and settle them down and let them go, there is a position of rest right in the middle where the swing is facing straight down. That's a position of rest. And the thing about periodic motion and oscillation is that that position of rest doesn't get to be achieved very much because of the momentum going through it. So in a pendulum or a kid on a swing, the pendulum is high, and then it has momentum going forward because of the acceleration of gravity. And then as it moves forward, it passes right through that rest position, and it doesn't stop. It keeps going. And then it winds up developing so much pull from gravity that it has to stop. And then gravity accelerates it back the other way, and it goes right through that position of rest, and it keeps going. Bouncing springs are the same thing. You have a mass hanging from a spring. You pull the mass down, you let it go, and it bounces. And that bouncing is one extreme position and another extreme position. And in between somewhere is a rest position that it would be at. If you were to grab the spring and let it settle and then let go, it would find some position of rest, but it can't ever achieve that in periodic motion because of the momentum of the motion. It carries it right through that position of rest. Okay. Some terminology. The distance from the rest position to one of the extreme positions is the amplitude. So, little brother on the swing, thank you, Nico.
Excuse me.
Little brother, little sister on the swing, they're sitting on the swing, you grab the swing, you pull them back, and then before you let them go, the distance from the height that they've been pulled to, from the distance that they began at, that is the amplitude. And then you let them go and they start swinging, and then you could stand back with a stopwatch and time how long it takes for them to go from where you released them all the way forward and all the way back again. And that would be the time of one period. A period is the amount of time it takes to go through one cycle of oscillation. Okay? So the amplitude is the distance, the period is the time, and then if you take the inverse of the period, you wind up with the frequency. So the inverse is something you maybe not, you're not as familiar with in math, but if you divide 1 by some number, you have its inverse. So if your period is 3 seconds, you take a kid, you drag them back, you let them go, they swing, and it takes 3 seconds to go forward and back, then their period is 3 seconds. Their frequency would be 1 divided by 3, which would be 0.33333, whatever. And that would be their frequency, their hertz, the number of cycles in a second instead of the number of seconds per cycle. So the frequency is the period raised to the negative first power. It's the inverse of the period gives you the frequency. Hertz are good for very small amounts of time. If you've got a really long period, like 3 or 4 or 5 or 10 seconds, or a big pendulum that might have a period of, 20 seconds or something like that, then hertz are not as meaningful because you're dividing 1 by 20 and you're getting a very small number. but we use hertz a lot when we have a very fast period and we want to make that number a bigger number that we can work with better. So dividing 1 by a very, very small number gives you a big number, instead of dividing by a big number gives you a very small number. And you'll see some examples of this in a moment. What's wrong? You weren't done. I'm sorry. I'll go back. Okay. That's okay. So here we have again these terms that we just defined. Let me give you pictures for them. So a pendulum, the maximum swing, the extreme right position, the distance from here to here would be the amplitude, and then it swings back to the extreme left position, and the distance from here to here is also the amplitude. So amplitude is from the rest position to one of the extreme positions, okay? And we measure that in some sort of metric measurement. In this example, it's in centimeters. It's usually in meters. But the distance from rest to an extreme position. You can also measure the amplitude of a spring. You have a mass on the end of a spring. You pull the spring down, you let it go. It bounces and bounces, and the distance that it goes up or down from the rest position is the amplitude. Okay, so distance of displacement is the amplitude. And then the period is the amount of time it takes to complete a full cycle. So grab your little brother, drag him back on the swings, let him go, and this amount of time is 1 period, okay? Grab the mass of the spring, drag it down, let it go, and this amount of time is 1 period. Period is the amount of time in one oscillation. A frequency is the opposite of that, the inverse of that. It's 1 divided by period.
It does look like a swing.
Sorry, what?
Kind of does look like
It does look like a swing. That's
yeah,
why.
or the ride, the one, the crank.
Oh, okay. Yeah. Yep. Periodic motion is caused anytime a system with a restoring force is disturbed. A restoring force is something that wants to bring something back to rest. So in the example of the swing that we keep going to, the restoring force is gravity. Gravity wants your little brother in his swing to be straight underneath the bar and the chains going straight down. And gravity wants it down. Gravity is the restoring force. But you have disturbed gravity by taking your little brother, dragging him back, and letting him go. And that now gravity doesn't have it the way it wants it. And so gravity tries to get the little brother back to the middle, but every time he pulls on your little brother, he winds up swinging to the other side, right? So periodic motion is caused anytime a restoring force is disturbed. Again, this example with the spring and the mass, this time it's the pulling up of the spring that is the restoring force. And gravity is also a restoring force. Now the spring and gravity are working against each other. So you pull down on the mass, and the spring is like, no, don't stretch me. So the string pulls back up. But he pulls past the rest position because of momentum until gravity grabs it and says, no, you pulled that too far. Now gravity pulls it down, and the spring says, no, I want it up, and gravity pulls it down. So in that case, you have 2 restoring forces, right? And they're trying to get the mass to be back in the middle. Periodic motion is caused anytime a restoring force is disturbed. So let's do a little bit of math. We love math. Math is good. Math tells us that the mass of the object in periodic motion affects the period t, okay? And so t is equal to some spring constant, some restoring force, and we'll worry about what that is later, times the square root of the mass. And that is true for a spring sort of system, not for a pendulum. We'll get to a pendulum in a minute. But for a spring sort of oscillation, the amount of time it takes for the mass to go up and down is controlled by the spring constant times the square root of the mass. And the spring constant K is something that is different for every spring. You've got to measure what that is, and then you'll know it in the future. Okay? So if the spring constant for a spring were 6, and the mass were 4 kilograms, then you would say 4 square root of 4 is 2 times the spring constant of 6. It would take 12 seconds for that spring to go up and down. Very slow oscillation. Okay, so it's pretty simple math. It's not hard math to do. And then when we look at a oscillating system, a system that's got periodic motion going on, there are things that slow down these periodic motions. So one example would be friction, another one would be gravity. So if you take your little brother and you pull him back on the swing and you let him go and you don't push him, and he doesn't know how to pump yet. So he's just a lump of dead meat at the end of the chain, right? And he's swinging. And he's just saying, yay! But you don't push him. Eventually, he's not saying yay anymore. Eventually he looks back and he says, Andy, push me, right? Because he's not swinging anymore. And the reason that he doesn't keep swinging forever is because there's friction in the hinges of the chain, and there's friction in every link of the chain. And so every time he moves, some of the energy of his motion is absorbed by friction. And there's also gravity, and gravity is what's driving the system, but gravity also wins a little bit on every swing so that he's oscillating closer and closer to the middle. Gravity and friction and things like that, wind resistance, slow down an oscillating system, slow down a pendulum, slow down a little brother on the swing. And we call those things damping forces. Not dampening, because that means they're getting wet. But damping means they're slowing down. And so friction and things like that slow down an oscillating system. An ideal oscillating system, in theory, would keep going forever. But in the real world, things slow down, right? Little brothers on the swing don't keep swinging forever. Otherwise, it'd be a great way to babysit tell your kids to get babysit. Go to the park, put them on a swing, go like this, and then go have dinner. And you come back in an hour and a half, and they're still going like that and smiling.
Or
That
they're
would be
gone.
wonderful. Or they're gone. Yeah.
Sorry.
But damping forces slow down oscillating systems. So in the real world, nothing goes forever. And then resonance is when an outside force increases the amplitude of successive oscillations. This is when you push your little brother. Little brother's on the swing, you let him go, and then the next time he comes up to you, you go like this. And the reason you did that is because you're adding some more energy to his oscillation so that the friction in the chain and the friction in the hinges and the air resistance and gravity, you're adding a little more energy to that every time so that he keeps swinging, right? This is why kids say, push me, push me, push me, push me. Because you have to overcome the damping force. You have to be resonance. You have to be adding a little bit of energy each time. Now, if you just add enough energy each time to overcome damping, then you're going to continue the oscillation indefinitely. And that's why you can get stuck behind your little brother or sister, pushing them on the swings for a long time. Because, this never has to end. But you can also add more resonance than the damping force is taking away, in which case you're increasing the oscillation each time. That would be every time your little brother comes back, you like shove him really hard, and then he goes higher, and then he comes back, and you grab and shove him really hard, and he goes even higher, and eventually he's going around the bar, right? Yeah. So that would be, it's called a driven oscillation, but that's where the resonance is greater than the damping force, okay? And you're driving the thing further. Yes?
I have a story. So, my auntie.
Here we go. Here's a spring oscillating with a mass, the maximum position, the minimum position, and the rest position, okay? And as it's going up and down on this, we could analyze the spring constant for K and predict the time and all that kind of stuff, right? And again, with the pendulum, the amplitude and the rest position are here, and so you can see amplitude applies both to springs and to pendulums. And I don't know why I have these pictures after this slide and not originally. I think I meant them to be earlier on, but we can see that springs and pendulums both operate this way. Here's a damping force, right? If the displacement is originally very large and the amplitude is big, but every time it oscillates, the amplitude gets smaller, then this oscillation is being damped. And the damping force we could analyze, and we could look at how much it's changing every oscillation. Okay, so this is an example of a damped oscillation. This is the opposite. This is the opposite. An example of a driven oscillation, where you're adding some resonance. Every oscillation gets bigger. This is like pushing your brother on the swings, and every time he swings, he gets further and further away, and eventually the oscillation is very large. So this is damped and this is driven. A driven oscillation requires resonance, requires something pushing. Okay. Specifically, a pendulum. We're going to talk about the math regarding a pendulum and some terms associated with those. A pendulum is a mass attached to the end of an arm with a pivot point. We call the mass a bob. So if you know anybody named Bob, he's a pendular mass. Yep. And if you take Bob and you put him on a swing, then it's a perfect pendulum.
I know a builder named Bob.
Bob the builder.
Yeah.
Yeah. This reminds me of one of those. What do you call a person with no arms and legs jokes? Yeah. What do you call a person with no arms and legs? They're the string. Bob. Huh. Yeah. It's also the same answer. What do you call a man with no arms and legs in your pool? Bob. Anyway, a mass called a bob is attached to the end of an arm. The arm could be rigid, or it could be flexible. It could be rope or string or a chain, or it could be an actual rigid arm. And there's a pivot point at the top. That's a pendulum. The period of the pendulum is determined by this formula, which is a little different than the spring constant one. Oh dear. 2 pi times the square root of L, which is the length of the arm, divided by G. Okay, and so the length of the arm, L, there is how long the bob is from the pivot point, and then 2 pi never changes and G never changes. So really, the only thing that controls how long it takes a pendulum to swing back and forth is the length of its arm. So you could have a very massive bob on a short string and have a very small bob on the same length string, and those two objects would oscillate at the same period. Okay, or you could have the same mass on different strings, and even though it's the same mass, you would oscillate at a different period. The length of the string is the only thing that controls how long it takes a pendulum to swing. So you can use this. Restaurants probably don't find it amusing, but if you want to know how long a chandelier's chain is, going from the height of some big fancy ceiling down to a chandelier, and you want to see, how high is that ceiling? You can swing the chandelier, and then time how long it takes the chandelier to swing, and then use this little simple formula, and you'll know how high the ceiling is. It's kind of fun. Don't recommend that in fancy restaurants because they're going to go, "What are you doing?" Just curious to know how high your ceiling is. I'm going to do some math.
I wouldn't suggest that in a less expensive restaurant either.
Well, why not? Especially if you swing it this way, and then you start going with it, and then everybody around you is going to get seasick. Yeah, anyway. So 2 pi times the square root of the length of the arm divided by G, which is the acceleration of gravity. So the mass of the bob does not affect the period of its oscillation. Okay, so here we go. This is just an example here. Here we have a pendulum, and the length of the arm from the point of suspension to the center of the mass of the bob, that length is the length here, right? And so you just need to know that, and you can do the rest of the math and figure out how long it will take, or if you know how long it's taking, you can do the math and figure out how long the arm is. Okay, do I show you the shortcut? I don't. Let me show you just a little bit of a math shortcut here real quick. What's pi? 3.14. 3.14. Multiply that by 2 real quick in your head. What's that?
624. No, 628.
6.28. Okay. So 2 pi is roughly 6.28. divided by the square root of the length of the arm over g. G is 9.81, right? What's the square root of 9.81?
3.32. No, right? No.
1.9.
It's really close to 3.1, actually.
Oh.
Really close to 3.1. It's 3.2 something. So pi is 3.14, and the square root of g is 3.2 something. So you can actually take the pi out and take the g out, and mathematically it's almost the same thing. It's not perfect, but it's really close. So this helps you with your, I'm standing in a restaurant and I swing my chandelier and I want to know how long the rope is. If you know the period, it's essentially 2 times the square root of the length of the arm. Because you can take this out and take this out and have almost the same number, a very close number. And so you wind up with 2 times the square root of L as a quick approximation. It's not the right answer on an exam, but if you want to see if you're just doing mental math, 2 times the square root of the length is almost the same number as 2 times pi times the square root of the length divided by g. It's almost the same. Okay, that's it. Any question about pendulums? No. So next time you go to the playground with the swing, which you can actually do as a menu assignment this week, you can do a little bit of math at the playground and feel smart. Okay.
We're done?
That's it.